We have only got 2 contestants left, so I'd like to welcome contestant number 6. Could you please put your hands together from Deryck Chan from the east of England?
Can't let me know I'm one take. Can't let me in your head. I'm not here to make a deal, but it's praise that I get. You ain't gonna walk free, boy. Now I finish with you, yeah. No, can you feel the warmth? Yeah. As my kiss goes down, you like some sweet.
Good afternoon. My name is Deryck Chan, and today I'll talk to you about salad spinners, or in scientific terminology, a centrifuge. The global challenges of urbanization and climate change are pushing us to construct in ways that are novel, with new materials and techniques to build infrastructure that can withstand complex natural hazards like earthquakes and flooding. And sometimes the situations are so complicated that the methods of analysis and design themselves need to be calibrated experimentally. So how can we do an experiment with a new construction scenario without spending all the time and resources to build a full-scale trial and in the process putting workers' lives at risk because it might collapse? The answer is to use a salad spinner. You see, most physical processes, in terms of their safety and serviceability of most construction, is driven by gravity. And as I throw this confetti, you can see it takes a certain time for the confetti to travel a certain distance. The confetti represents soil and structural materials, and the air resistance represents the flow of groundwater. Now, we put this confetti in a salad spinner and spin it like this instead. You see, the confetti goes to the air straight away. This is a demonstration that when you increase gravity, mechanical processes happen faster and distances will feel shorter. Now, make the salad spinner bigger, and you have a geotechnical centrifuge. The photo I've got on the back is the Cambridge University Geotechnical Centrifuge, the largest centrifuge in the UK. It allows us to impose 100 times Earth's gravity by spinning a model about this big at a spin radius of over 4 meters. The dimensional similarity works out so that if you do that, if you make a 1 in 100 scale model, spin at 100 times Earth's gravity, it will have the same behavior as a real-life structure, with the added bonus that time travels as if it's 10,000 times faster. We have a time machine. We can use this to predict the gradual movement of a basement or a tunnel in London clay for several years after construction with a day of experiment. We can observe the collapse mechanism of a reinforced slope without putting anybody at risk. It's a lab experiment, by the way. Therefore, we can measure whatever we want: movement, bending moment, force, pressure, anything we need to inform our construction design. The possibilities are endless, and that's why, over the last few decades, the technique of geotechnical centrifuging has been perfected into a tried and tested method to push the boundaries of civil engineering and construction methods one experiment at a time. So, if this pitch interests you, come along to Cambridge or another geotechnical centrifuge center, have a spin with us, and may the centrifugal force be with you. Thank you.
Thank you so much, Deryck. That was a fantastic final line. That was very enjoyable. We've got a question there from Imogen.
Thank you, Deryck. I was about to say I'm going to get very distracted by your salad spinner. So obviously you've got the opportunity to test real-life conditions before people are going out on site. What do you think some of the positive impacts for sustainability are in using, trying to have wider usage of laboratory testing before we're going out on site?
The greatest advantage of doing this as a lab experiment rather than a field test is that you can test everything to collapse if you want. And that means we have an exact idea of how much capacity our construction method or structural combination actually has. And so we can test where the collapse point is at. And so we know that all of the rest is a safety margin, and that helps us really optimize our safety margins, which will have great sustainability impacts because we can save a lot of material and labor and all the construction processes that are now no longer needed because you know exactly where the limit point is.
Perfect. Thank you.
Thank you. Do we have a question from the audience for Deryck? Oh, yeah, up at the back. Thank you. Come on, Georgina, look quicker.
I'm glad I wasn't running down for it. Thanks very much, Deryck. One of the problems that I foresee is the fact that soil is it's not uniform as a material, and when we're using such a small amount of soil in the test, how do we ensure that the soil that's in the test in the centrifuge is representative of the soil that we're actually going to use in the field?
Yep. In our centrifuge lab, we have equipment that is specifically designed to make our soil uniform, controllable, and reliable. So for example, when we pour a dry sand sample, we have a robot that automatically pours the sand so that we can get the density and grain packing that we want. And we have methods both to control how the nozzle displaces the sand and we have weighing scales to check the density of the sand that came out. And for fine grains of clay, we have automatic hydraulic presses and automatic stirrers that help us make the clay very uniform, and we do it in a vacuum so that all the air bubbles get purged. And in the process, we can make sure that we can be repeatable in all our experiments and make sure that we have a valid scientific experiment that can then be used to test a general theory and then apply the results to a construction site. Yeah, thank you.
Thank you, Deryck. Can we get our final round of applause, please, for Deryck Chan?